Hello friends, in this video we will build a semantic search engine. Now let's imagine we have a bunch of documents like these here are some Wikipedia articles, and we would like to search for a topic. So we would like to find out all the articles which contain information about that particular topic. So traditionally what we do is we do the keyword search for the topic. So we search for the keywords in all these documents, and then we will find out how many keywords appeared and how many times appeared. Based on that analysis, it will return the documents, the search results, right? That's the traditional way of searching using the keywords. But one issue with that is now some of these documents might actually be relevant to the topic, but they may not have the exact keywords we are searching for, right? In that case, those documents get ignored or excluded, right? So in such a scenario, semantic search, which is based on what the user intent as well as the context of the search words, it will return more accurate and better results. But as you can imagine, compared to the keyword search, this is much more involved. Okay, because we need to understand the semantics of and the intent or the context of the search. Okay, so in today's tutorial, we will build a semantic search engine using a vector database. So this is the overall architecture. For example, we start with a bunch of documents, and then we have an AI or embeddings model, which what it does is it converts all these documents into vectors of fixed size. For example, depending on the model, this model might convert a given text or document into a vector of size, let's say 1000, right? Now, then all these documents are converted into the vectors, okay, of the same dimension or the same length. Now, after converting or creating these embeddings for the documents, we insert or index these vectors into a vector database. Now, vector database, it's a special kind of database. It's a purpose-built database with mainly two objectives. One, the retrieval of the vectors or the information from the vector database is very fast, because typically these vector databases, they contain the millions or even billions of records, right? For example, imagine a database with all the Wikipedia articles, or maybe millions and millions of images. We might be trying to find a particular person images, etc., right? So number one, the information retrieval or the data retrieval is very fast in vector database. And the more important one is, in vector database, these vectors are indexed again using some AI algorithms such that they are stored in a way so that the similar documents they are grouped together. Okay, the similar documents, they sit near to each other. So when we query the vector database, we can find the similar vectors very easily and very quickly. Okay. Now, to do the similarity, to measure the similarity, there are different measures like cosine similarity, Euclidean distance, dot products, etc. But in most cases, we will use the cosine similarity. So which is basically, so we have a vector like this, we will have another vector, let's say those two represent these two documents. Now we want to find out how similar these two documents are to each other. So what we do is we measure the cosine similarity between these two vectors. Okay, so that's how we do. So in step number one, we take all these documents, we use an embedding model to create embeddings or the vectors, and then we index them in the vector database. So that's how we build the vector database. And then during the applications, we have a query or we want to search for something, right? So the document or text, we again apply the same embedding model so that we get another vector of same dimension. Now using this vector, we query the vector database. So we will find out what are all the vectors which are close to our reference or query vector using the cosine similarity. Now, depending on how many results we want back, we will find out the top 3 most similar vectors uh, corresponding to our reference vector or query vector. Now we can map these vectors back to the actual documents. So this way, even if we have millions and millions of documents, we can very quickly find out all the documents similar to our search result or the search document. Okay, so that's the overall, that's the very high level architecture, how this works. Okay, so as I mentioned, we need a vector database to carry out this. The rest of the things we can do it using open source AI/ML models as well as Python, but we need to have access to a vector database. So for this tutorial, we are going to use Pinecone. Okay, it's a cloud-based vector database, and I find it very useful. I mean, there are dozens of vector databases recently because of the AI advances. But Pinecone, I find it's one of the top vector databases. Okay, so here we can create a free account. Just go to the website and register, and then create an API key, because we need the API key to interact with the vector database using our Python. Okay, then you can create a project. Here I have a free account, so I can create only one project. That's why I'm not seeing create, this is being disabled. But the free account will serve our purpose. So I have already created a project called My Experiments. Okay, so if I go here, and here we'll create indexes. Again, for free account, we can create only one index, because only one pod, or let's call this instance, database instance, is allowed in the free account. But if we have an upgraded version, we can have multiple projects, and then we can also create multiple indexes in each project. Now, index is simply the database. Okay, in vector databases, it's usually referred to as index, but read that as a database. Okay, now we'll come to this UI again. So let's go to the code, and yeah, okay, all right. So we need some data. We need a model to convert our data, the text, to embeddings, and we need a vector database, right? So let's install 3 libraries. So the first one is to interact with the Pinecone client, and the datasets library, we can use it to access a number of datasets related to text, images, audio, etc., etc. And then sentence transformer, we use this library to convert our text or documents into embeddings. Okay, all right. So let's load this dataset we are loading this Cora dataset. Now this is for demonstration purpose. Now it has millions of documents or the text. We don't know all of them. So here we are just picking some 50,000 documents or text. So throughout this tutorial, I will be using text or document interchangeably, but I will be referring to the same thing. Okay, so here we have loaded the dataset. Now let's look at the first 5 records. Okay, so the first record, it's this first record. This Quora, as you probably know, people ask questions on Quora, right? I mean, different people ask different questions. Sometimes it's the same question, but asked by a different person in a slightly different way, but it's referring to the same question. So this data set is to train ML models to detect if 2 questions are referring to the same thing or not. Okay. So for example, if you look at here, the first record, it has the question ID. So here are the 2 IDs, and these are the 2 questions asked by 2 different users. Now, as I mentioned, this data set is created to develop AI/ML models to detect if 2 questions are the same or not. But that's not what we are going to do, but we are just making use of this data. So what we do is, we get rid of all these IDs, etc. We simply want this as one text or document, and this one as one text, another text and document. And similarly, this one would be another text, and this one would be another text. So basically, we want a corpus of text or documents. Okay. So here we just manipulated the records so that we can get all the documents as a single list without the pairs, right? So here we are looking at the first 6 records. So this is the record number 1, or the text 1, text 2, text 3, and text 4, etc. Right? And you remember here we have loaded 50,000 records, and each record contained 2 questions, right? So we should have 100,000 records, but here we have removed the duplicate questions, so the exact duplicate questions. So we end up with 88,000 plus questions or the documents. Okay, so all we have done, I mean, we don't have to worry about this Quora, these questions, etc. All we have done up to now is we have installed these 3 required libraries, and then we created some data in the form of this, in the form of a list, right? And each element is a document or some text, let's call it. Okay. And then, so we are going to use this sentence transformer library to import a model which can create embeddings from text. Okay. Now this code, it's simply checking if the hardware I am running has GPU or CUDA. I'm running on my local machine, so it does not have. So everything is going to be running on CPU. Okay. So from the sentence transformer, this is the model we are using. So it's this mini LML model. It can simply convert the given text into vectors. Okay. Now there are 3 things important. So here we are printing some information related to the model. So the first one is max sequence length. This is important, 256. So if we give a text of tokens which roughly translate into the number of words more than 256, it cannot convert into embeddings, or it will ignore all the words or the tokens after the token number 256, right? So it will use only the first 256 tokens to convert the text into embeddings. Okay, that's important. And also the second one, word embedding dimension 384. So given a text which is below 256 tokens, it will create a vector, and the vector dimension would be 384. Okay, so whether the text has only 10 words or 100 words or 200 words, the created vector or the embeddings will have only 384, will have exactly 384 points, or that's the vector dimension. Okay, and finally, not so important, but here the created vector, it's a normalized vector. Okay, so it means the unit length, the vector length will be 1. Now, as I mentioned, we will be using either cosine similarity or dot product or Euclidean distance, etc. When computing the similarity between the vectors. Now, if the vector is normalized, the cosine similarity and the dot product will result in same distance because the denominator, which is the length of the vectors, is unity. Okay, but this is not so important. All right, let's take one example document and let's see how we convert it to an embedding. Okay, so let's take this text. Which city is the most populated in the world? Now this model, this is our embeddings model. So here we have embeddings model, which is this mini LM model from sentence transformers. So we just simply say encode and we give the query. Okay, and this XQ will be the vector. So if you look at the shape, it's a of size 384. Now let me show you the vector. So as you can see, this is how the vector looks like. So because it is normalized, all the values are below 1. Now if you take if you compute the length of the vector, that will be equal to 1, and this will have 384 points. Okay, 384 numbers are that's the dimension of the vector. Okay, so that's how we can take some text and we can use embedding model to convert this text or document into a vector. Okay. All right. Now, when we insert the records into Pinecone vector database, it expects the vector in this format, right? It expects three elements. The first one is ID. This can be some simple serial number. Okay. So, for example, the first vector or the document, let's say we start with 0, and then the embedding vector, and finally the metadata. So we can have some metadata. This metadata can be the text itself or maybe some tags, etc. Now these metadata, it can be useful when we want to convert the vector back into the text or image, or we might have some tags. We want to do further filtering, etc. Okay. So once we compute the vectors, we have to prepare the list in this format so that we can insert into Pinecone. Now this is very specific to Pinecone. Different vector databases, they might expect the input format to be different. Okay. All right. Now, okay, so we need to create a database in our index in the Pinecone, right? So here we are importing Pinecone. And then, so I already have my API key as well as Pinecone environment. So I got them from the Pinecone website, as I mentioned here. So you can go to the Pinecone website, and when you go to API's key, so here you will find out the environment and also your API key. So take those two values and you can put it in your bash profile file or wherever you want, and you can read those two values using the environmental variables. Now here we initialize the Pinecone. Okay, so here we initialize the Pinecone. We have made the connection to it, right? Now we want to create a database, which is what I showed here. So this is my project name. So under this project, I have already created this semantic search engine search database or the index, right? So here our index name is semantic search, and then here we are searching if here we are getting all the indexes which exist. As I mentioned, in free version, we can only have one index, but let's say we have a paid account and we have multiple vector databases, etc. So we are, before creating this new index, we are making sure it not already exist. Okay. So once we check that it did not exist, now we are creating the index, right? Now here, these three pieces of information is the most important one. And obviously we need to give the index a name. So we need to supply a name. And then the second one, we need to tell a Pinecone what's the dimension of each vector going to be. Okay. So as we saw in our case, this particular model, this particular mini LM model, it's going to create vectors of dimension 384. Now here we can either give the number 384 directly, or we can get it from the model, right? So this is our mini LM model, and the vector dimension, we can get it using this attribute. Okay, so that's the vector dimension. And finally, we need to inform the database or the index how we are going to measure the similarity between the vectors. Okay, so here we are using the default one, the cosine similarity. Now this is most important. The reason is, depending on this, when we insert the data, how we insert the data into the database is determined by this. So when we upsert the data, we simply call a command upsert into the database. But there is a lot happening behind under the hood. So depending on this metrics, vector database use different algorithms to structure the data so that the retrieval becomes faster, and the similar vectors, they sit near to each other, so that we can get the similar vectors quickly. Okay, so that's why we need to inform the similarity matrix when we are creating the index itself. Okay, so with all this, here we are creating the index. Okay, so we have created, we have accessed the, or we have connected to the index. All right, now we need to convert the documents into embeddings and then insert into the vector database. Now, if you do one by one, because we have 88,000 documents, it will take quite a lot of time. And also, we cannot do all at the same time because that would require a huge RAM, right? So that's why we do in batches, right? So here we have chosen a batch size of 128. I mean, you can choose a different number. So what we do is we take 128 documents at a time, and then as we saw here, we need to create three things before we insert the vectors into the embeddings into the database, right? So we need to create an ID, we need to create embeddings, and we need to create the metadata. Okay, so what we do here is, so with this loop, we are selecting 128 documents each time. And then here we are creating the IDs, which is simply the serial number. And then here we are creating the metadata, which is simply the text itself. Okay. And here we have created the embeddings. Okay. So the three pieces of information, IDs, metadata, and the embeddings we created here. And then we group them in this format because that's what the Pinecone expects, right? The Pinecone expects the vectors in this three element format, right? In this three element format. So we used this Python zip function to prepare the data. And finally, we are doing the upsert here. So this is where we are inserting the records or the embeddings into the vector database. So as I mentioned, under the hood, a lot happening with this command. So depending on the similarity matrix, some structure or the way the data is stored can be significantly different, so that the retrieval as well as finding similar vectors becomes easier and much faster. Okay, so yeah, so with this loop we have inserted all the records into the database, and now with the describe index, it will return us the dimension of each vector and also the total number of vectors we have. So it's about 88,000. Now this index fullness, I'm assuming it's probably referring to the size of the database. So 30% of the database is full with these 384 records. Okay. Now we have completed the first part, right? So for example, this part. So we have completed this upper part. We have taken some 88,000 documents or text. In this case, they happen to be questions. We have used mini LM embedding model to create embeddings, one for each question. This is of dimension some 384, each vector 384 points, like here we have 4. And then we have created a vector database, or we have created an index in Pinecone, and then we have inserted these 88,000 embeddings into the vector database. And before doing that, we prepared the data in the format expected by Pinecone, which is the ID, the vector, and the metadata itself. Okay, so this upper part is done. Now, when it comes to the application, what we do is, so we might have a question, we want to find out similar questions, right? In this case, so we take that question, we apply the same embedding model so that it output a vector of size again 384. Now we take this vector and we query the vector database for similar vectors, and we return top n vector. Depending on whether we want 1 vector, 3 or 5, we will return those vectors. Now from the metadata, we can map the vector or vector IDs to the documents, which in our case, the questions, right? So that's what we are going to do. So here we have a question. Now the first thing we need to do is we need to create the encodings, right? Or the embeddings. So we are using the same model to create the embeddings. Okay, we converted this to a vector by using this toList command, right? And then here we are querying the vector database. Again, under this command also, a lot is happening. What we are doing is we are using the newly created embeddings for our query as an input, and we are supplying two additional arguments. How many results we want back? It's 3. We are asking for top 3 results, and here we have the option to get the metadata or not. Okay, but with this one, again, a lot happening under the hood. So this vector, it goes to the vector database, and the cosine similarity is computed between this vector and all the vectors within the database in a more structured way, so that we can compute the distance with all the vectors, and it can return the top n vectors. Okay, so this is what it has returned. So the results, it has an ID, obviously, and then the metadata, which is the text itself. This is what we inserted when we created the database. And importantly, we have the score here. Okay, the similarity score. So the similarity score will be between 0 to 1. So 1 means those two vectors are very close. I mean, exactly similar, but closer to 1 means those two vectors are very similar to each other. Okay, so here is the second result, slightly lower score, but again, you will have the ID as well as the text, and similarly the third one. Okay, so we'll just format this result so that understanding it becomes easier. So all we are doing is we are simply printing the score as well as the text. Okay, so these are the three results we got. So let's have a look at our reference or query again. So which city has the highest population in the world? Okay, let's see what 3 results we got back. So what country has the biggest population? Yeah, it is semantically similar. Okay, looks good. And then we have the second one as what is the most isolated city in the world with over 1 million metro area inhabitants. So this is again referring to the population. Now the third one, which is the most beautiful city in the world. Now, please be careful here. I mean, as we said, for a reference text or document, the vector database simply return the top 3 semantically similar documents. Now it might happen that this our reference query might not be semantically similar to any of the 88,000 vectors we have in the database, right? So even in that case also, it still return the top 3 matches, right? So that does not mean all 3 matches will have to be exactly semantically similar to our reference query, right? So depending on the size of the database, depending on the type of the data, all results might make sense, or maybe only the top one makes sense, etc. Okay. All right. Now let's look at one more example. So here we have which metropolis has the highest number of people. Okay. Now here, as you can see, we have used the word metropolis instead of maybe a country or city. And also instead of using the population, here we have used highest number of people. Now, if it is an exact keyword search like the traditional searches are, we will be searching for metropolis in all the documents, right? And if a document does not have metropolis, we might ignore that. Whereas with the semantic search, it can understand we are referring to a geographical area. So it will not be searching for exactly the metropolis word. It will be searching for a geography, whether it is a country or city, etc. Right? So that way, a semantic search can understand the intent as well as the context and can give more accurate results. So for this one, here we have the third one, what country has the biggest population. And then this one, it's again similarly referring to with over 1 million metro area inhabitants. Okay. Now, what is the most dangerous city in the US? Probably not good compared to the rest of the two, but I guess you understand how the semantic search works. Okay. All right. Now, if you want, you can delete the index as well. So if you run this command, the index get deleted. Now let's go back to the Pinecone UI. So under experiments, here you will see, sorry, this is the project. So under this project, you will see all the indexes you have created. So in our case, this semantic search. Now, again, some standard information. So Pinecone, in this case, is using Google Cloud Platform. Okay. And it's a free environment. The two important pieces here are the dimension of the vectors 384 and the distance metric is cosine similarity. So this is what we gave when we created the index, right? So it has these 88,000 documents plus documents. Now the part fullness, I guess it is again referring to the memory. Now there is a lot of information, so depending on the queries you are doing, etc. So here you can see how the number of vectors evolve over time, because the number of vectors don't have to be constant, right? We can keep adding more and more vectors as we get more documents. Okay. And then how many requests we are making and how they are evolving over time, etc. So we can have all those statistics here, right? And whatever we can do programmatically, we can do from the UI also. So from here as well, we can upsert the records. We can add new embeddings. We can query them. We can update. We can delete the records also. Okay, but we probably don't be doing this from the UI. But at least these pieces of information, like how the vector count evolve over time and the number of requests, the latencies, etc., how the database is performing, can be very useful. Okay, that's all for today. Now, with the advancements in AI, the vector databases have lots and lots of applications, not only in the language, in the images, audio, etc., in all forms of data, even including the tabular data. So in this video series, we will be looking at multiple applications of vector databases. Okay, thank you very much.